will be discussing today on macromolecules, which comes under Unit 4. What are macromolecules and part of polymers, what it is impacting our day-to-day lives, and of polymers life, how it will be, and what are the disadvantages of these polymers. So our dependence of polymers in the form of plastics or toys or various materials, it has been very widely used. And one such polymers, are many polymers which are day to day, it's being used is one such as Teflon rubbers or Teflon tapes or pipes or billiard balls or files and so on. So how do we define a macromolecule? A very large number of molecules which contains thousands of atoms. We refer it as macromolecule. And a part of macromolecule is a polymer, which is large molecule composed of many repeating units called as monomers. So these are the monomers. When they form, if all are having same monomers, we call it as homopolymer. If we have multiple monomers, we call it as a copolymer, or at least two sets of monomers, we may call it copolymer. And if we have multiple monomers, depending on the thing, we can make it as friction-based polymers. And so as discussed, macromolecule is the one where large number of molecules contain thousands of atoms, and a large molecule or macromolecule with a number of repeating units. And monomer is the one which is referred as a building block or repeating unit. And polymers can be, or macromolecules can be natural or can be synthetic. So polymerization is a process by which macromolecules form from several monomer molecules with different molecular weights. As discussed, there are several naturally available polymers or synthetic polymers. So depending on the monomers, whether they are formed like linear fashion, we call linear, or even branched or even cross-linked kind of polymers. These are several synthetic polymers like polyester, amides, polyethylene, or styrofoam, or polyacrylate, as compared to polysaccharides, peptides in the case of natural polymers. So there are several natural polymers which are like from day-to-day activities like wood, starch, or DNA, rubber, and so on. Then there are a lot of understanding or improvements in order to improve some properties where synthetic polymers are being made. Coming back to the polymers term was first proposed by Berzelius, a German organic chemist. So where he has demonstrated the existence of macromolecules and characterized as polymers in the year 1922. So, and he has been awarded Nobel Prize in chemistry. So polymers which are repeating units contain monomers, and the process of unition of molecule is called as polymerization. So this is one example. If you take ethylene gas, we polymerize, we get polyethylene, which is widely used for plastic bags. So you can see that this ethylene, if we polymerize, we get polyethylene. And how do we call polymers as high molecular weight, monomers, and so on, or units? So when the molecular weight is somewhere between 5,000 to 2 lakhs, you refer it as high polymers. And also these high polymers are called macromolecules because of the high molecular weight. So anything molecular weight is lower than or in the order of 2000, we call it as oligopolymers. And the extent by which the polymers is called as degree of polymerization. So there are not necessarily homopolymers. We can have heterogenic polymers like polyethylene dipeptide, where you have oxen functional groups, or inorganic like polydimethyl-siloxane, which is also referred as PDMS. So we can classify polymers based on the form and its used, source, or also based on biodegradability. Polymers based on the form and use, they are hard and tough depending on the utility. We refer them as plastics. There are several polyethylene, polyvinyl chloride, and so on. And depending on respect to elongation and good strength, we refer them as elastomers. Depending on the classification, where the polymers can be drawn into five filaments, which is like 100 times more of a length, we call them as fibers. And if you want like adhesives or sealants, a lot of epoxy based adhesives or polysulfide systems are there, which are called as liquid resins. There are several natural polymers, like you can see glucose, alpha D glucose units, which are multiple units are forming, which is referred as starch, or beta D glucose, which is referred as cellulose, or polypeptides, they are also referred as proteins, or styrene, for example. In this case, it is buna rubber, or for example, styrene butadiene, not styrene, like um, butadiene sort of rubber. And classify polymers based on man-made versus natural ones. So here, there are several artificial polymers or synthetic polymers like ethylene, polyethylene, propylene, or any polystyrene resins, several kind of polymers. Depending on the biodegradability, also one important factor where biodegradability of the polymer also plays an important aspect, where this is one such biodegradable polymer, and several polymers which are synthetically made are mostly non-biodegradable polymers. One very important aspect of polymers is how the orientation of these monomer units when they are polymerized. So this is referred as tacticity. It's all about how the orientation of monomeric units takes place, whether they are in same side, the side groups of the monomer units are in the same side of the polymer chain, then we call it as cis arrangement, which is also called as isotactic polymer, for example, natural rubber. If the arrangement of side groups are in alternating fashion, which is more like a trans arrangement, you call it as syntotactic polymer. If the monomers are in random arrangement, those is referred as atactic or heterotactic polymerization. Even there are several examples for this. So tacticity is a very important property. It makes big difference in the polymer. And one such importance about is polypropylene, polyethylene with Ziegler-Natta catalyst. They have so different properties as compared to uh, the arrangement, stereo arrangements and so on. If the depending on the tacticity, it can be either very rough or it can still sticky gelatinous plus lumps can also be formed. So one such tacticity you can understand is isotactic, syntotactic, and atactic. You can see in the case of polypropylene, all the carbon atoms or like methyl arrangements for the propylene are on the same side of the configuration. Then it is called as isotactic. In syntotactic, you can see there is a periodic arrangement of the atom methyl here and then methyl. So this kind of regularly changing the configuration, you call it as syntotactic, and it is a very randomized system, you call it as atactic kind of systems. So atactic polypropylene is soft sticky, and isotactic polypropylene is it can crystallize and it can even form like thin fibers and sheets. So you can see in the case of polystyrene, polystyrene we have a isotactic where all the styrene units are in one side. Here it is alternate and it is very randomized. We call it as um, tactic kind of atactic polystyrene. We have seen how polymers can be classified and polymers are being differentiated based on tacticity and the source and what do you, the biodegradability kind of classification and so on. Now let us see how to make these different kinds of polymerization reactions. So we will look at what are the different kinds of polymerization reaction can happen, what are the preparation and properties and the applications of several polymers. So these are the four prescribed polymers which we have. So this polypropylene in addition to polymerization category, polystyrene, PVC, and Teflon. So polypropylene can be synthesized by polymerizing propylene using Ziegler-Natta polymerization to get polypropylene. Okay, so this is how the propylene is polymerized, and we get a stick or fiber kind of metal where the melting point of this polymer is close to 160 degrees. It has got several applications in dishwashers, food containers. Again, we can make isotactic or atactic depending on the density of the polymer and how these things are. And also here one important aspect is Ziegler-Natta polymer is a very important role towards making isotactic polymer. Okay. Even in the year late 1978, cars front bumper used to be made from polypropylene, and basically, as we already discussed, we can have isotactic, syndotactic, and atactic kind of categories for polypropylene. One very important aspect about this Ziegler-Natta. So we know that if you use a catalyst, it decreases the activation energy, thereby accelerating the reaction without being consumed into the reaction. So these are the very important combinations of very important contributions of the Ziegler-Natta catalyst, for example, like titanium chloride, aluminum chloride, ethyl aluminum as the catalyst. So it follows by initiation, propagation, and termination reaction, where we have a catalyst which is being added to polypropylene molecules, where the catalyst adds itself and then it attacks some polymers, some more monomers to form propagation step. And when two of these radicals, when they are mixing or upon action of um, hydrohalides or like that, we get polymer along with recovery of the catalyst. So polypropylene belongs to a group of olefins, and it is partially crystalline and it is non-polar. So it is similar to that of polyethylene, but it is harder and it is more heat resistant. And there are several uses of Ziegler-Natta controlled polymerization of polypropylene, and we can make especially isotactic, syndotactic kind of polymers, and several not easily possible with branching and so on. This polymerization can be used. If you use Ziegler-Natta catalyst, where we are bringing down the high pressures and high temperatures, we can come back with room temperature and very low pressures. So this is the importance of how Ziegler-Natta heterogeneous catalysis will control the stereospecificity of polypropylene. One more set of polymer which we have is polyvinyl chloride. So if we take vinyl chloride and heat in presence of benzoic peroxide, we get polyvinyl chloride, and it's a free radical polymerization reaction. And the usage is enormous with respect to pipes or even clothing and so on. It is coming to the properties of polyvinyl chloride. It is non-flammable and a chemically inert powder, and it's colorless. It is very much resistant to acids, polar solvents, and bases. One problem with this polyvinyl chloride is it dissolves in chlorinated solvents or more like non-polar solvents. That is the reason it has got tremendous applications in flexible tubing with these advantages, and for insulation and for water pipes and raincoats and so on. Set of addition based polymers is Teflon. So we have tetrafluoroethylene. If you polymerize using a peroxide initiator, we get Teflon. So, or there are other ways by which we can remove the chlorine, which is called as dechlorination, decarboxylation, okay, CO groups removal, or if we take CF4 and by electric arc, if we do, we get Teflon. And so once we get the Teflon, it has got the properties similar to that of other polymers, where it is highly crystalline polymer with high melting point, and it is very resistant to acid, bases, strong hot acids, and so on, and very robust with respect to temperatures like -100 to 350 degrees. Due to which it is very widely being used as insulating materials for motors, cables, and so on, and also for a lot of packaging materials and non-stick grids. So these are some of the widely used, and these are also called as hydrothermal bombs or solvothermal bombs, where you have a Teflon containers where we in the sealed environment to do faster reactions, and these are pellets which are coated with Teflon, and all of you are aware of this Teflon pads. One set of not strictly adhesion polymer is polystyrene, where it is one of the oldest and most widespread polymers in the world. So, coming to there is a history on this, where it was isolated in the year 1839, and it's the most widely employed thermoplastic kind of polymers. So many of you are aware of styrofoam or polystyrene. So this is hard, brilliant, transparent resin. So we take styrene and polymerize, we get polystyrene. So depending on the arrangement of this benzene or like styrene or vinyl, or we can have isotactic, synotactic, or atactic kind of polystyrene with various, and even though the glass transition temperatures are slightly variant in this case, the melting point, there is a lot of difference. Polystyrene gets easily dissolved in several aromatic hydrocarbon and chlorinated solvents, and it is generally used for various sterilizing test tubes and for a lot of diagnostic components, and is also widely used for food service industry, as for example trays, containers, and so on, and also for lining for a lot of thermal insulation cases, fridge and freezers and so on. So these are some of the adhesion-based polymers: propylene, polypropylene, and its applications; vinyl chloride to polyvinyl chloride for various applications; and Teflon towards utensils, cooking pans, and so on; and styrene to polystyrene. These are the polymers where addition reactions, where we won't see any molecules are being lost. Now we'll see a set of reactions where we do a condensation polymerization, where we get polymers, we see elimination of molecules. So under condensation polymers, we have four different categories: nylon, PET, polyurethane, and synthetic rubber. So polyurethane and synthetic rubber are not strictly condensation-based polymers. These two will be more suitable towards condensation, but we will discuss more about this when we come across. So it is very important to understand the functionality of polymers. In other cases, what we have seen is carbon-hydrogen bonds, carbon-fluorine bonds only. So in order to undergo polymerization, molecule should have capability to react either by applying pressure or so on. So there should be at least functionality of at least two atoms. So the more the reactive groups or bonding sets are present, monomer functionality. For example, if a monomer has OH, carboxylic acid, amine, thiol, or isocyanate kind of groups, and significance of functionalities with respect to cross-linking or functionalities are totally variant. So if we have bifunctional monomers, we get a linear polymer. Trifunctional monomers, we get a cross-linked copolymers, depending on how the branching and this one is formed. We will look at first condensation polymer, which is nylon, and its history. So nylon 6 was it all started, the birth started of nylon 6 when it appeared in the form of women's stockings. there are like some food sold in few hours. Um, then this is how it can be synthesized. We can take hexamethyldiamine and adipic acid. We get nylon 6,6 by elimination of water. Okay, so one hydrogen from here and one OH from here will be taken out, and then we get nylon 6,6. So nylon 6,6 refers to 6 from hexamethyldiamine and 6 carbon atom adipic acid. And both of these adipic acid and hexamethyldiamine can be obtained from adiponitrile. If we hydrogenate adiponitrile, we get hexamethyldiamine, and if we hydrolyze adiponitrile, we get adipic acid. There are several exceptional properties of which is very strong, stiff, and it's a replacement for silk. That is what people looked into that, and these are absorbance and easy to wash are some of the important attributes of this nylon. The first chain length talks about amino chain, and another one talks about the acid chain. So we can also have nylon 6 based on food is taken from polycaprolactam or caprolactam. One more is polyester, where we can use terephthalic acid, methylene glycol, where we get ester. We have ester linkages like this. So here, it's a dicarboxylic acid in a diol reaction, and different brand names PET is being generally used. Both of them are aliphatic kind of thing. The resultant polyester will be aliphatic. These are aromatic. One is aromatic and aliphatic. So you can see terephthalic acid in methylene glycol giving PET, and we can see the elimination of water when we have a polymerization reaction, and this is the repeating unit. This is also called as polyester. It melts around 265 degrees and is resistant to heat and moisture, and it is generally being used for fiber reinforced plastics or coatings. And this is not like completely rearrangement reaction, it's more of a polyurethane. It's composed of organic units joined by carbothioneate units. So you have an isocyanate, diisocyanate, plus a diol, both the H2. Polyurethane, where we say an isocyanate and alcohol to the nitrogen, oxygens are linked to the and where we get this urethane kind of linkage. So the polyurethanes generally they display thermosetting properties. So polyurethane is one such material where it exists in various forms like foams, rigid, flexible, and so on. So depending on the end user applications, it can be for insulation or cushioning, or for example, cars, spare parts, or adhesives, rollers, tires, or any sports related things. This is one such material which no other plastic will make the same way as polyurethane has been made, depending on the kind of applications like cushioning, shoe soles, or panels or artificial hard walls. The reasons for which it is being there is very widely being used. Last set of condensation, again it is not strictly condensation polymer, is rubber styrene dimethyl. Shortage of natural rubber has started, where people started to use synthetic in various chloroquine or neoprenes. So one such thing, like chloroquine polymerization giving rise to neoprene. So one such advantages or research development in this category is styrene butadiene rubber, where if you add butadiene, styrene butadiene rubber, it's like a copolymerization kind of reaction because we have two which giving rise to styrene butadiene. The usage of polyurethane in various fields like towards lining jutes or clothing industries or to like and automobile based things for brakes to all zippery, all these things will be very much for towards polyurethane. And other than this important property to understand is when we talk about crystallinity of polymers, it has to do with um, how these linear chains are being arranged. For example, this is the arrangement of molecular structure of these are the carbon atoms and these are the hydrogen atoms, and how these chains are arranged in this is in a unit cell is shown clearly here. And aspect polymers after non-addition and condensation reactions are what are thermoplastic kind of polymers. So thermoplastics are the polymers. When we heat them, they soften, and when we cool, they become harder. So which can like reversible sort of things like so many linear-based polymers like polyethylene, polystyrene, PVC, or branched polymers are examples under this category. In the case of thermosetting polymers, they are once they heat, they become hard, and once they are cooled, they are not going back to the. So because of network polymers and the covalent bond present into this, uh, we get this thermosetting kind of polymers, and most of the epoxide, phenolics, and polyesters are typical examples. So in the case of thermoplastics, since a linear polymer, there are no cross links. When we heat them, between the polymer chains, the weak forces are easily broken, so which they can be again cooled down, they come back to the original state. Since there are no cross links between them and there are weak attractive forces, these the chains between them are when we are heating it. So change of shape can be remolded back upon cooling. So the weak forces restoration is something very new in the case of thermoplastics. In the case of thermosets, because of the cross links present, when we heat them, they go to a place because of the strong covalent bond between the polymer chains. Chains cannot be easily broken because of extensive cross linking and the chains slippery uh, moving, sliding over the road, which makes the polymers thermosets. Not just if you look at thermoplastics, if you look at molecular level, when temperature is raised, secondary bonding forces and sliding the movement and adjacent chains will state the stress being applied. And we have a lot of irreversible degradation when molten thermoplastic polymer is highly when we apply high temperatures. A lot of linear polymers are the examples of thermoplastics. In the case of thermosets, develop network polymers and a lot of extensive crosslinks and also covalent bonding, generally harder and stronger as compared to thermoplastics. For example, several rubbers, epoxides, and phenolics are the typical examples of thermosetting polymers. Very important attribute of the glass transition temperature, where the polymer experiences a transition from rubbery to rigid state is called as glass transition temperature. The below the glass transition temperature, it becomes hard, above which it is soft. Okay. So the hard brittle state is glassy state and the soft flexible state is rubbery state. Polymer with high molecular weight also the crystalline also plays an important role in glass transition temperature. These are some different polymers, addition, condensation based condensation based polymers and copolymers, and what are being applied in applications and different brand names towards applications. And these are some of the addition based polymers and what are being used, for example, polyester or polypropylene, where it is being used. different rubbers, elastomers like isoprene, where it is being applied, and styrene butadiene rubber copolymer, and with different brand name, GRS, GUNA-S rubber are being widely used. Very important attribute to understand is how polymers, certain polymers in the monopolar solvents, they get dissolved. And so it's very important to understand the chemical resistance. Polar solvent will dissolve polar polymers, non-polar like light dissolves light. Non-polar solvents will dissolve non-polar polymers, okay? Because it causes swelling, softening, and loss of strength. Okay? And also cross links, especially with the thermosets, will reduce the solubility of the polymer. Interested readers can look into these NPTEL platforms. Also, the textbooks on university chemistry and engineering chemistry books, followed by the web links towards understanding that kinds of polymerization process and what are changes and the modifications, types of